Hello everyone. Welcome to the European Non-Associative Algebra seminar. Today is August 7, and we have a talk by Lleonard Rubio y Degrassi from Uppsala University, Sweden. He's going to talk on Hochschild cohomology groups under gluing idempotents. Please.
Okay, thank you very much, and thank you very much. So first of all, I would like to thank the organizers to give me the opportunity to speak at this online seminar. It's a great pleasure. So today I will be talking about mainly the first Hochschild cohomology and the relation with gluings of idempotents. All of this is joint work with Yuming Liu and Chan Wang. So the plan of the talk will be mainly to introduce Hochschild cohomology, and in particular the first Hochschild cohomology, try to motivate the study of Hochschild cohomology, and then in the last part of the talk, I will be discussing some of the results that we have in joint work with Liu and Wang. So yeah, the main reason for this is because I was not sure how much the audience was knew about Hochschild cohomology. Okay, so let me start by fixing some notation. So for me, K will be an algebraically closed field. Then I will usually denote by A and B to be two finite-dimensional associative K algebras. Hochschild cohomology will allow us to pass to the non-associative world, but we will start with associative K algebras. Then I will denote by N a non-negative integer. Then J of A will be just the Jacobson radical of A. Then, so one can study algebras up to many equivalences. One can study algebras up to isomorphism, but in a more categorical framework, one of the first steps that one can take is try to study algebras up to Morite equivalence. So this means if we have two finite-dimensional algebras A and B, then we say that A and B are Morite equivalent if the K-linear categories of finitely generated modules mod A and mod B are equivalent. So this was studied by Morita, and the notation that I will be using is just this. I will say that A is Morita equivalent to B, and then I will denote this tilde superscript M to denote this type of equivalence. So there is proposition that is due to Morita that will be also, it's useful to remind this proposition, because then we will talk about more general equivalences. So we say that A and B are Morita equivalents if there is an equivalence between A and B, a Morita equivalent between A and B, if there are two bimodules, which I will denote by M and N. So M is a AB bimodule, and N is a BA bimodule, such that the following two condition holds. So the first one says that M and N are finitely generated and projected at left and right modules. And the second condition is that if we take M and we tensor over B with N, then we obtain a bimodule, which is isomorphic to A. And similarly, if we take N and we tensor over A with M, then we obtain a bimodule, which is isomorphic to B. Okay, so I'm giving some introduction to, let's say, finite-dimensional algebras, and I'm also trying to take the direction that I would be interested in this talk. So one can study algebras up to Morita equivalences, and this we will see that this reduces to also, in some sense, study algebras in a bit more combinatorial way. So let me introduce some notation that hopefully is familiar to some of you. Otherwise, let's try to introduce quite rather quickly. So by Q, I will denote a finite quiver. So a quiver is an oriented graph, which means that we have a set of vertices, which I will denote by Q0, and I will have a set of arrows, which I denote by Q1. Finite means that the set of arrows and vertices is just finite sets. Then one can consider paths, which I usually denote a path by the letter P, which is given just by a concatenation of arrows. Could also be arrows or paths that are coming from the vertices, which are called lazy paths. Then we will need some notation. So we have this concatenation of arrows usually, and I denote by S of P just the source of P, so the vertex in which the path starts, and by T of P the target of P, the vertex in which the path ends. We will see an example very soon. I need also a couple of more notation that will be useful much later in the talk for the results that I have with Yuming and Chan. So the first notion is, so we take a vertex and we say that a vertex is a source vertex if it does not exist an arrow alpha such that the target of alpha is equal to this vertex E. So a source vertex looks like this, so there are no arrows of this form. And dually, we can define the notion of a sinc vertex. A sinc vertex is a vertex for which does not exist an arrow beta such that the source of beta is equal to E. So a sinc vertex would look like this, and there are no arrows of this form. Okay, and so then one having this path, one usually what can construct is the path algebra. So a k-vector space has basis just the set of paths. And so as the name suggests, this is an algebra. It is an associative algebra. And the multiplication is given by concatenation of the paths. Okay, so maybe it's a good point now, if you have never seen such notion, just to give you some examples. Well, we will have just one example, which will be our guiding example throughout the talk. Okay, so we have this quiver here that has 3 vertices. We have these 3 arrows that are labeled by alpha 1, alpha 2, and beta. And so we can observe that this E1 is a source vertex, and then this En is a sinc vertex. Then there are these dotted or dash lines, depending how you draw them. And so this indicates that there are some relations, meaning that one, for example, can consider the path alpha 1 beta. So this is one of the paths that one can construct. Another path that we can construct is the path alpha 2 beta. And so what we can form is the ideal generated by these paths, which we will call by I. So the ideal generated by this path, what we can do with this ideal is take the path algebra and then quotient by this two-sided ideal, and we obtain an algebra which has k bases given by the set of vertices and the set of arrows. So we are just killing this path here. So this will be our algebra A, which will be our guiding example. So as we have noticed here, we start with some combinatorial datum, which is given by just a quiver. We can introduce some ideals, and we can construct an algebra. So the question is every algebra of this form? And well, for answer to this question, maybe let me introduce the last piece of the notation in this setting. So I denote by RQ the ideal generated by all arrows in Q. And so the answer to this question was given by Gabriel. So if we take A to be a finite-dimensional associative algebra, so now I always assume the algebra to be associative, then any algebra is Morit equivalent to a path algebra quotient some ideal. So we require some condition on this ideal. So this ideal must be admissible. So this means that there exists m, positive integer, m greater or equal than 2, such that it sits in between the square of this arrow, this is usually called the arrow idea, so the square of the arrow ideal, and the power of this arrow ideal for some m greater or equal than 2. Okay, so in the case that we have the example that we have, one can check that we had an admissible ideal. Okay, so now we have all the first ingredients that we need from associative algebras. Now we can introduce the notion of Hochschild cohomology. So the nth degree Hochschild cohomology of an algebra A, this is usually denoted by HHN of A, and can be defined as follows. So the following definition is given in more homological terms. So let me start with that. So we can consider A as a AA bimodule, which the structure of a bimodule is given by left and right multiplication, who equivalently is just a module over its enveloping algebra, which I denote by A superscript E. So the enveloping algebra is just A tensor over A of the opposite algebra. So we consider A as a bimodule, or as A module, and then we consider the projective resolution of A. And this gives us a chain complex. Then we apply the contravariant Hom functor with coefficients in A and gives us a cochain complex. And then the nth cohomology of this cochain complex is defined to be the Hochschild cohomology of degree n. This is a rather abstract notion, maybe for some of you. So luckily for us, we will be mainly interested in HH1 of A, and this has a more intuitive description. So in fact, let me start with HH0. HH0 of A is just the center of the algebra, while HH1 of A can be described as the set of derivations of an algebra quotient the set of inner derivations of A. So this, as I said, will be the main focus for us. So let me define what the set of derivations of an algebra is. So this is what you expect. These are just k-linear maps that go from A to A, which are k-linear, which satisfy the Leibniz rule, namely f of A times B is equal to f of A times B plus A times f of B for every A and B in A. And then the set of inner derivations are just derivations. They are induced by an additive commutator. So more precisely, this is given by f, are just maps that go from A to A, which is a derivation such that, well, there exists an element B in A for which f of A is equal to B times A minus A times B for every element A in A. Okay, so we have this space, which is the quotient of the derivations, quotient by the inner derivation. And this has a very nice structure. It's now a Lie algebra. So the reason why it's a Lie algebra is because the whole Hochschild cohomology is a Gerstenhaber algebra. So in particular, this means there is a graded Lie algebra of degree -1. So this implies that HH1 of A is a Lie algebra. So how the Lie bracket is defined? So let me take two derivations, f and g. Then the bracket between f and g is simply given by f composed with g minus g composed with f. So we have f and g to be two derivations of A. Okay, then we have even more structure in characteristic P. So if the characteristic of the field is P, then the first Hochschild cohomology of A is a restricted Lie algebra. So we just need to define how the p-power map is given by. So we denote the p-power map of a derivation is just given by taking the derivation and composing by itself p times. It's worth noting that in general, if we compose derivations, we don't get derivations. But in characteristic p, if we compose p times, this works. Okay, so maybe now that I give you the definition, let me follow our guiding example. So let me assume for simplicity that the characteristic of the field is different from 2. And let me consider the quiver that we had before. So we have this quiver E1, E2, we have 3 vertices. We have alpha 1, alpha 2, then we have beta. We have these 2 relations that I just described before, and we recall that A is just KQ quotient by this ideal I. Okay, so then one can show that the derivations of A are just isomorphic to the case linear space given by the following. So we will have f of alpha I, alpha j, and f of beta. For I and j, there are either 1 or 2. So let me just note as well that this is a very unconventional notation, but in order not to introduce more background, we will just follow this type of notation. But let me explain what this map do. So these maps do. So f of alpha I, alpha j, evaluated at an arrow gamma, or at any path that we can have in A. So let me just say is alpha j if gamma is equal to alpha I and is 0 otherwise. So in simple terms, this means that this is basically a map that sends an arrow alpha I to the corresponding arrow alpha j. And similarly, f of beta of gamma, this should be beta beta, but just to simplify a bit the notation, will be beta if gamma is equal to beta and 0 otherwise. Okay, and so then the set of inner derivations are just isomorphic to f of alpha 1 plus f of alpha 2 alpha 2, and then f of beta. So the more, if one wants to follow the normal notation, this would be by following Strammetz's notation that I will not discuss today. But for us is that one can show that HH1 of A is just isomorphic to SL2K. And this is the reason why I need the characteristics to be different from 2. Okay, so far we started with an associative algebra. We obtained this Lie algebra. And so one would like to have some motivation to study Hochschild cohomology. So one of the main motivations is that Hochschild cohomology is invariant under various categorical equivalences. For example, invariant up to Morite equivalences. Now we will introduce a more general equivalence, and we will see that it is also invariant under this equivalence. But also it's worth noting at this point that Hochschild cohomology is not functorial. So if I give you an algebra and a subalgebra, say an algebra A and a subalgebra B, then it's very hard to relate in general HH1 of the Hochschild cohomology, or the first Hochschild cohomology of A and B. Okay, so this is just something to keep in mind for the end of the talk. So let me first define this new categorical equivalence. So we first define the stable module category. of finitely generated A modules, which is usually denoted by A underline mod. And so how is defined this category? Well, has the same object as the category of finitely generated A modules. And then we just need to consider the morphisms. And the morphisms are given by, so what we do is we consider the same A module, a homomorphism, but we quotient by the morphism that factors through a projective A module. So more precisely, we denote the morphisms in the stable module category by A underline from N to N. So M and N are just two modules. And so we take from M to N, and we quotient by P A from N to N. So this means that P A from N to N, this just denote the A homomorphisms from A M to N that factor through a projective A module. Okay, so the idea is that in this category, in some sense, we kill the projective modules. And then we define stable equivalence. So if the stable module categories of A and B are equivalent, and I mean equivalent as k-linear categories, then we say that there is a stable equivalence between A and B. Okay, and so this stable equivalence, the notion of stable equivalence is very general. In fact, if you have a Morita equivalence, this implies that you have a stable equivalence. But in general, it's hard. Since they're very poorly understood, the Brouwer introduced a stable equivalence of Morita type. So it's in some sense Morita equivalence in the stable module category. So we will see that we'll have the same, almost the same condition of a Morita equivalence. So we will have two bimodules for which we will tensor, and we will obtain a very similar conditions, but slightly different because we need to take into account that in some sense we kill this projective modules. So this definition is due to Brouwer. And so if we let A and B to be finite dimensional K algebras, and then we take two bimodules. So I will use now the same notation that I'll be using Morita equivalences. So we take these two bimodules, M and N. So M is a AB bimodule, B is a BA bimodule. Then we say that M and N induce a stable equivalence of Morita type and between A and B if the following two conditions are satisfied. The first condition is exactly the same condition that we had for Morita equivalences. So let me just write it down. So M and N are finitely generated, projective as left and right modules. And then the second condition is slightly different. So if we take M and we tensor over B with N, then we obtain a bimodule which is isomorphic to A, but in this case we allow to have a projective bimodule P. So this is as AA bimodules. And then similarly, N tensor over A with M is isomorphic to P plus some Q, which is a projective BB bimodule. Let me just write, so P and Q are just bimodules, projective bimodules. Okay. Let me also introduce some notation. In the case of stable equivalences between A and B, we denote this by SE. And then for stable equivalence of Morita type, I will denote this by SEM. Let me also remark that we have the following chain of equivalences. So if we have a Morita equivalence, then one follows from the definition, basically, that we have this induces a stable equivalence of Morita type. And then this implies that we have a stable equivalence more generally. Okay, and now I introduced these new equivalences, so let me now state a result that links this with Hochschild cohomology. So this is a result due to Koenig, Liu, Zhou, and of Briggs, myself, that says that if we take A and B to be finite-dimensional, symmetric K-algebras, so symmetric K-algebras, symmetric means that A is isomorphic as an AA bimodule to its dual. If you want an example, which maybe is the best thing to have at this point, for example, group algebras or finite groups are symmetric algebras. So if we have such type of algebras, and if we have a stable equivalence of Morita type, so the nice stable equivalences in some sense, then this implies that HH1 of A is isomorphic to HH1 of B as restricted Lie algebras. So the results of Koenig, Liu, and Zhou, and of Briggs and myself are more general. So let me say in this case, so what is due to whom? So for the Lie algebra isomorphism is due to Koenig, Liu, and Zhou, and then for the restricted part is due to Briggs and myself. And this holds, of course, for the whole Hochschild cohomology and the graded Lie algebra structure in that case. Okay, so, but this, for us, let's say that gives us motivation for the invariance. So this implies in particular that if, you have a Morita equivalence between two algebras, then Hochschild cohomology is an invariant and will allow us maybe to identify various classes of Morita equivalence, or more generally stable equivalence of Morita type, or yes, so stable equivalence of Morita type. But as I said, stable equivalence of Morita type are a particular class of stable equivalences. There are other classes of stable equivalences, and now I will introduce another class that is in the what we are interested in joint work with Liu and Wang. Okay, so let me first give you a definition. This is so far maybe the notion has been slightly more abstract. So this stable equivalence is more concrete, is more combinatorial sometimes. So that's why maybe it would be nice to define this. So let A and B be two finite-dimensional K-algebras. Then we define the notion of a radical embedding F that goes from B to A. This is simply an injective algebra map such that it sends the Jacobson radical of P to the Jacobson radical of A. So they have the same Jacobson radical. So this radical embedding allows us to see the algebra B as a subalgebra of A. And also, now for simplicity, we assume that A is of the form path algebra, quotient some admissible ideal I. So then there is a remark due to C that says that each radical embedding let's say F that goes from B to A can be obtained by a finite sequence of subalgebras. So we start with the algebra A, we call this algebra A0, then we pass to A1, then up to AS for some S, this will be our B. How do we obtain AI plus 1 from AI? So this is obtained from AI. So recall that all these algebras can be described as a path algebra quotient some admissible ideal. So this is by identifying two vertices E and E prime in the quiver of AI and putting the old or the relations in AI plus the newly maybe and the newly formed paths through E, which is now equal to E prime. So this is a bit of a wordy remark. So maybe the best thing to do now is to give you an example. So now you understand what is happening. It's very simple. At each step, we just glue in two vertices, and then what we want is that the Jacobson radical must be the same. And so what we do is just we add some relation that allows us to obtain so. So the example that I'm going to give you, it will be our guiding example. So let me start maybe a bit more space. So, okay, so we have E1. So if you remember, we have E2. And then we have another vertex, E3. Then we have alpha 1, alpha 2. Then we have beta. Then we had these two relations. So if you recall, I was just generated by beta alpha 1 and beta alpha 2. So what we can do now is we can glue two vertices. So in our case, we will glue a source and a sink. So this is a source, this is a sink, and we're going to glue these two vertices. So what we say is we glue, maybe it's a bit, so we glue E1 and E3. Okay, maybe let me move a bit this quiver here. So what we obtain is just a quiver which will have just two vertices, F1 and F2. And so we have glued E1 and E3. So this becomes the same as this one. So this will be denoted by F1. Then I will denote this arrow by alpha 1 star, this arrow by alpha 2 star, and this will be our beta star. And now, what we want is the Jacobson radical of these two algebras to be the same. So we need to add the new relation because we are forming new paths. For example, we can do beta star, alpha 1 star, we can compose these two, and it is non-zero, whilst here we could not compose beta with alpha 1 star. When we cannot compose, which means that it's zero, the composition. So the new relations that we add are just, as I said, beta star, alpha 1 star, and then beta star, alpha 2 star. So these are the new paths that we can form in this quiver that we could not form in the quiver QA. So maybe let me call this QA and this one QB. Okay. We can also, so far, let me show you another example. So far, as I said, we can also, we have only considered quivers with one connected component, but we could have more than one connected component. In algebraic terms, this means that the algebra decomposes into different blocks. So let's say that we are thinking more in topological, if you want, graph theory. So let's consider the following quiver. So the labeling will be a bit strange, but the reason for this labeling is just, or the vertices is for the last theorem that we will have. So in this quiver here, we have a quiver with 4 vertices and 2 connected components. And so what we can do is to glue E1 and E4. We are gluing this vertex with this vertex. And what we obtain is our guiding example. So we will obtain a quiver of this form. So this will be alpha 1 star, this will be alpha 2 star, this will be beta star. This will be F3. This is F1, and this is F2. Okay. Okay. In this case, there are no relations for this quiver. Whilst in this case, we need to add some relations because, again, we can concatenate these two arrows and these two arrows to obtain new paths. And so we impose that the relations, so what we can do is we can concatenate, for example, alpha 1 star with beta star and alpha 2 star with beta star. Okay, so this is basically what we do at each step of our radical embedding. So we can split the radical embedding into a sequence of steps of this form. Okay, now that we know what we mean also by gluing two idempotents, we have the following result due to Koenig and Due. So if we let F to be just a radical embedding, and which is obtained by gluing a source vertex and a sink vertex, which is, for example, what we have seen in the example. Then we have a stable equivalence between A and B. So if you remember before, the first Hochschild cohomology was an invariant and the stable equivalence of Morita type. So now the question is the first Hochschild cohomology an invariant under these equivalences? So the natural question to ask is, what is the relation between the first Hochschild cohomology of A and the first Hochschild cohomology of B? So ideally, we would like to have an isomorphism, but in general, one can ask this more general question. Okay, so what we can do now, and basically what we did at the beginning was just to check for some examples. And so let me take the example, the first example that we had here. So let me just copy and paste this example. You could also just call it example 1, but yes, let me just paste this one. So in this case here, what we have, so if you recall, HH1 of A was just isomorphic to SL2K. If the characteristic of the field is different from 2, well, then it turns out that if one does all the computation, then HH1B is just isomorphic to GL2K. So we have one interpretation of this is that, well, actually, HH1A is just a quotient of HH1B. But this seems one family of cases. And then one can also take the other example that we have just seen before. And for this example here, maybe 1 second, let me just squeeze maybe this here. Yes, so for this example here, this is QA, this is QB. Then we know already that this algebra here, so in this algebra here, we have added these relations here. So we know that HH1B is just isomorphic to SL2K, always assuming the characteristic different from 2. And one can check that actually also HH1A is isomorphic to SL2K, because basically the only part that gives us SL2K is what is called the Kronecker quiver, whilst the HH1 of this part is just 0. Okay, and this is a nice guiding example that basically shows and gives us the idea for the main result. So let me state one of the main results that we have. So we let A to be a finite dimensional. So now we are adding one assumption that was always in the example. So the finite dimensional algebra is monomial. Monomial means that the ideal that we are quotienting by is generated by paths and not linear combination of paths. So the finite dimensional monomial algebras, and then no, it's just one algebra, and then we let f from B to A to be a radical embedding obtained by gluing a source vertex and a sink vertex. So I let me just label the vertices. So the source vertex, I call this E1, and the sink vertex is En. There is, let me just state here, but for simplicity, there is one extra case, there is one exception to this theorem, but I will not state it here, and it just appears in characteristic 2. So then, and it's just one algebra. So we have the following result. So if E1 and En are from the same block, so this means from the same connected component, then the first Hochschild cohomology of B, quotient by an ideal J, is isomorphic to the first Hochschild cohomology of A as restricted the algebras. And we also have an explicit description of this ideal J. Just let me say that this is a one-dimensional ideal. And the second case, which is the second example that we have seen, if E1 and En are from different blocks, then the first Hochschild cohomology of A is isomorphic to the first Hochschild cohomology of B, again as restricted Lie algebras. Okay, so let me just finish by saying two things. In our paper, we also consider, one can also define in general the gluing of two arbitrary vertices, and we have also results in that direction, and also for high Hochschild cohomologies, we have we have other results. But in terms of Lie algebras and restricted Lie algebras, these are probably the most relevant results. And let me also just say, the last thing is that we have seen before, I told you before that Hochschild cohomology is not functorial, but in some sense, for this case, where we see B as a subalgebra of A, we obtain some sort of functoriality. So we can relate the first Hochschild cohomology of A and the first Hochschild cohomology of B. Okay, so I think I'll stop here. Yeah, thank you.
Thank you very much. Other questions? Let me see in the chat. Nothing. Okay, if no questions, let me thank you once again for your interest in talk. And thank you for everyone for participating in our seminar, and we'll resume next week. So see you.